In this problem, we have a population that starts at 40 and is growing 12% each year. The fact that it's growing the same percent each year implies that an exponential model would be appropriate to model the situation. The question is, how many years will it take this population of 40 before the population reaches 240? So I'm going to write a population model. I'll call it P of t. The population starts at 40. To get it to grow 12% per year, my b value will be 1.12. I'm going to use the variable t as an input variable because it represents time. Now the question is, how many years will it take before the population, the output variable, reaches 240? So I'm going to replace P of t with 240. This leaves me with an exponential equation. I know it's an exponential equation because the variable is in the exponent. Here's a four-step process to solve an exponential equation. Step 1 is to isolate the exponential expression. An exponential expression is a constant raised to a variable. So this is what I'm trying to isolate. I.e., I need to get the problem to look like some constant raised to an exponent equals some other constant. Right now I don't have that. I have a constant raised to an exponent times a number equals some of the constants. So I will need to take the 40 to the other side. Since the 40 is being multiplied, I will divide both sides by 40. Since 240 divided by 40 is simply 6, I'll simplify my equation by arguing that 40 divided by 40 is 1, so this simplifies out, leaving me with 1.12 to the t. And then what used to be on the left side of the equation, I'm going to move to the right. This was the number 6. So notice I have done step 1. I got the problem to look like a constant raised to an exponent equals some of the constant. My constant is 1.12. My exponent here is t, and where it says some other constant, that's simply the number 6. Step 2 is to take the natural log of both sides. So I literally plug in the left side of the equation into the natural log function. And then since I did that to the left side of the equation, I need to plug the right side of the equation, which is the number 6, into the natural log function. That's step 2. Step 3 says if the base is e, I'll ignore this line because my problem has a base of 1.12, which is not e. Step 3 says if the base is not e, that's my case, move the exponent down as multiplication. This is a property of logarithms that says that this exponent of t can be moved down in front as multiplication, and that would look like t times the ln of 1.12, and then I'm just copying the right side of the equation now. So I'm done with step 3. Moving on to step 4. Step 4 says to solve for the input variable. This is a simple step because I simply have some number times t equals another number, and since it is being multiplied, I can divide both sides by the ln of 1.12, leaving me with the answer that t is exactly equal to the ln of 6 divided by the ln of 1.12. If I was asked to give an exact answer, this would be it, but since I'm asked to give an approximation as a decimal rounded to 4 decimal places, I will need a calculator, and I will simply type ln of 6, close the parenthesis off, divide by the ln of 1.12, and to 4 decimal places I get 15.8103. Now I'm going to show how I could have gotten this without solving by hand. On the graphing calculator, I press y equals, I type in the equation that represents a population that starts at 40 and is growing 12% each year, so b would be 1.12. On the calculator, I have to use the letter x as a variable rather than t. As a second equation, since I wanted to know when the population was 240, I will type 240. Since I know I'm trying to see something as high as 240, I need to adjust my window by pressing window. Notice that my output, which is the letter y, has a maximum value of 10. I'm going to go down there and change that to about 300, given that I'm trying to find when the population reaches as high as 240. Now remember that my outputs represent the population, but my input variable, t in the problem, but I'm using x on my calculator to represent time, has a maximum of 10, and I'm not sure that 10 years is sufficient enough for the population to reach 240. So even though I know the answer is 15, I would have guessed, without even doing the problem by hand, that 10 years may not be enough. I usually change this to at least 30, 50, and sometimes even 100 to give the population enough time to grow so it reaches the desired value, in this case of 240. Now that I have my window set up, I'm going to press graph. Here's the graph of the exponential equation that starts at 40 and grows 12% per year. Then as a reference line, I graphed y equals 240, which would be nothing more than a horizontal line through 240. Now I'll use my intersect feature to find the value 15.8103. I'm going to go second, trace, which accesses this calc menu. Number 5 is the intersect feature, so I press 5. It will ask 3 questions. Is this the first equation? I'll say yes by pressing enter. Is y equals 240 the second curve or the second equation? Yes. I'll press enter. Then it wants me to guess. If there were multiple intersections, it would be important for you to put the guess near the one that you want. Given that there's only one on my screen, I can actually just press enter and be a bad guesser. You want to make sure that the calculator has the word intersection here. Notice, to 4 decimal places, I once again get 15.8103 as I did by hand.